Hello. Today we're going to look at proving that base angles of an isosceles triangle are congruent. And the way we're going to do this is through transformations. So the proof is already written for you, and I just want to go through and make sure that we understand each of the parts. And so first thing I'm going to highlight is the fact that the givens is the first thing that is used as you go through this, and what you want to prove is the final thing. And this is going to continue setting up our proof throughout. So here we're going to prove that the measure of angle B, and highlighting these really can help you, is congruent to the measure of angle C. So this is my end goal, and it should be what I'm trying to prove. The way they're doing it is they're going to construct an angle bisector AD. And so as I'm looking at this, they've drawn this line, and the conclusion that you can make from that is that I have now two congruent angles. And that's going to matter. So I have this part here and that part there. And what we're going to show is that rigid motions will map point B to point C. And the reason why we want rigid motions is because we know that rigid motions preserve angle and distance. Okay? So let R be the reflection, and I'm going to point out that this is really important notation for us as we try to keep clear the difference between a rotation and a reflection. So this little tiny R right here will be the reflection through AD. Through the reflection, we want to demonstrate that two pieces of information map B to point C and vice versa. And therefore, AB would map to AC, and AB is equal to AC. And this is attained from the preservation of distance with the fact that it's a rigid motion. Since A is on the line, as reflected, the reflection of A is equal to A. And we've seen that. It's like your identity, since it's on the line. Reflections preserve angle measures. Really key, important piece of information. So the measure of the reflected angle BAD equals the measure of CAD. And if we're looking at this as a result, the reflection of the vector AB, or the ray AB, is going to equal the ray AC. Reflections also preserve lengths of segments, and therefore the reflection of AB will have the same length as AB, and therefore AB is equal to AC. So the reflection of B is equal to the point C. So this part is the part that kind of attains the goal up top. The rigid motions will map B onto C. So this part is sort of been checked off. If we reverse each of the arguments, and instead of looking at point B mapping to point C, and we're looking at AB, and instead looking at AC, and this being AB, then we can basically obtain that the result of reflection of C is equal to B. The reflection maps rays to rays, and so the ray BA is equal to CA, and the ray BC is then equal to the ray CB. Again, since reflections preserve angle measures, the measure of angle ABC reflected is equal to the measure of angle ACB. And what we've done is essentially identified this is a 180-degree line, with the intersection of equal angles here and here, which allows us to state that the two base angles are the same. We can conclude that the measure of angle B is equal to the measure of angle C, and equivalently that the measure of angle B is congruent to angle C. In proofs, we can state that base angles of an isosceles triangle are equal in measure, or that the base angles of an isosceles triangle are congruent. And the reason why I highlight all of this for you is so that you guys can get sort of used to a different type of proof. This is very paragraph based, but each part is supported by the definition of a reflection, and that's the important part of it. Okay, so use this. You're going to reference it tomorrow in your notes, and thank you for your time. Bye.